more. So we're going to get started with the second talk of Andrea Montanari.
Okay. So in the last lecture, we proved this simple theorem about random matrices. Let me remind you. So we had matrix X. Matrix X that is D1 times D2, tau square sub Gaussian. And then we proved bound on the operator norm of the deviation from the expectation. And this was of order square root of D1 plus D2. And okay, so we saw one application of this to the spiked model. And what I want to look at today is an application to random graphs. So take a graph G that is from the Erdős-Rényi ensemble. Okay, so what does this mean? It means that I have n vertices, and edges are independent, and each edge is present with probability p, where p is some number between 0 and 1. And okay, what we want to look at is the adjacency matrix A. So this is a matrix, is an n by n matrix whose entry ij is 1 if and only if ij is an edge. Okay. So this is the adjacency matrix. And what the question is, what can we say about the spectrum of this adjacency matrix, about the eigenvalues of the adjacency matrix? Okay, so well, what is this matrix really? If you look at the random variable ij for I less than j, these are IID random variables, and these are Bernoulli P. In particular, if you look at the expectation of the adjacency matrix, this is just P times the all one matrix, 1, 1 transpose, right? An entry ij is 1 with probability p, so if you take the expectation, this is what you get. Well, one has to be careful about what happens with the diagonal, really, because, you can define the diagonal to be all 0 or all 1s. Truth is that it doesn't matter for what I'm going to do. So I'll assume here implicitly that the diagonal is set equal to p, and it doesn't matter, really. Okay? So this is what is the expected adjacency matrix. In particular, the spectrum of this matrix is very simple. The first eigenvalue of this expectation is exactly p times n, right? Because there is p, and this is a vector of length square root of n. 1 is a vector of length square root of n. And all the other eigenvalues are 0, right? So lambda 2 Okay. So now what does our theorem give us in this case? Well, we have Bernoulli random variables, so this matrix A, so Aij, the entries of this matrix are sub-Gaussian. Particularly, they are 1 sub-Gaussian. Why? Well, remember what was our definition of sub-Gaussian. Something is tau square sub-Gaussian if the probability of being larger than a constant times tau square constant times tau is basically e to the minus constant square, right? Something, okay, let me remind you, random variable x is tau square sub Gaussian if the probability that this is bigger than expectation of x plus, let's say, tau times t. This is less than, say, e to the minus t over tau square. If you want, we can put t over 2. Okay? And if we put here tau equal 1, if you have a random variable, so x, okay, it doesn't matter, this, okay, bounded by tau. So something that whose absolute value is bounded by tau almost surely is tau square. By this definition, is tau square sub Gaussian. Okay, the center is bounded by tau. All right, so in this case, you have something that is bounded by 1 also, so is 1 sub Gaussian. Okay, excellent. So what does our theorem tell us? Well, this is a matrix with IID entries apart from the symmetry. Therefore, our theorem tells us that with high probability, the adjacency matrix minus the expected adjacency matrix in operator norm is bounded by what? By some constant, say 10, times the sub-Gaussian constant, that is 1, times the square root of the dimension. Now we can say something about the eigenvalues of A. You will have one eigenvalue of A. So the eigenvalues of the expectation, there is one eigenvalue that is P times n, and all the other are 0. The eigenvalue of A must be close to this by a factor square root of n. So there is one eigenvalue that is about P times n. Okay. Plus square root of n stuff, and all the other eigenvalue must be here. Okay, say between 10 square root of n and minus 10 square root of n. Okay.
So we have not seen the part for the other eigenvalue. I mean, on the theorem here, we have just the part from lambda 1.
Sorry?
On the theorem here, we have just the result from lambda 1.
No, we have the result for all the other eigenvalue because we know that, okay, good question. We know that lambda I of A minus lambda I of the expectation of A is bounded by the operator norm of A minus the expectation of A. This was just Bayes inequality. So all the other eigenvalue in the expectation, they are centered around 0. They are stick at 0, but now they can wiggle around and they can go as far as square root of n. But as long as P times n is much bigger than square root of n, basically things look like this. There is one big eigenvalue and all the others are very small. Okay, so now I chose the okay, so in fact much more is known. So, for what I'll do next, this very rough information about the spectrum is sufficient. But just as a parenthesis, a lot is known about spectra of Erdős-Rényi random graph. There is a theorem by Vous, and then there is more recent work that refines this theorem by, okay, I don't remember all the authors, but one of the authors is Charles Bordenave and et al. Let's say et al. I don't remember all the authors. But what they prove is that if P is bigger than something, so I'll refer to the result of Vous because it's the one that I remember. So 1 as a log n factor. Then the following happens. Lambda 2 of A is 2 square root of Pn plus small o of times 1 plus small o of 1. And lambda n of A is minus 2 square root of Pn times 1 plus small o. So the spectrum is like this. There is the eigenvalue at Pn again, and then all the other eigenvalues are between 2 square root of Pn and minus 2 square root of Pn. Okay? So basically, roughly speaking, the two results are of the same type when P is of order 1, but when P goes to 0, it gives a much sharper picture, a much more precise picture. Particularly, that result doesn't tell you anything. The important feature of this result is what? Is that there is a gap between the leading eigenvalue and the second eigenvalue. This is the most important feature. The previous inequality gives us a gap only if P is bigger than 1 over square root of n. Instead, this gives us a gap for any P as small as polylog over n. And okay, the more recent work, what they do is that they improve this condition. Okay, so this is a nice result, but it's not really anything particularly, it's a nice mathematical fact, but it has implication for many statistical estimation problem, and I'll describe one that is the hidden clique problem. So this is an interesting problem. So let me define it for you. Okay, so this is a problem about a random graph, and I generate a random graph with a distribution that I'll call npk. Okay, so remember that in this case we had a graph G that was an Erdős-Rényi random graph. This is also called the planted model, and this is generated as follows. Okay, you have vertex set n. This is the set of the first n integer. And then for some k, for this k that is an integer, you choose S, a set S of vertices, uniformly random, with sides S equal k. So among the n vertices, you choose k, exactly k, at random. And then you put down edges that are conditional independent with this given S. So given S, they are independent with distribution, with probabilities. Now, I put the edges with probability 1 if both vertices are in S, and with probability P otherwise. Okay. So it's very simple. I have n vertices. I select k, and I connect any two pair of vertices in the set, and the other I do it as an Erdős-Rényi random graph. And for most of what I'll talk about, you can think of P1 half. P1 half is a good enough case. And the question is, given a realization of the graph G, find S. So I generate such a graph, I give it to you, and ask you, give me S. Tell me what S is. Okay? Is the problem clear? So this problem was introduced by Jerome, I think in '94. And it's a very nice problem because it shows in a very simple way some very deep phenomena about the interplay between statistical estimation and computational complexity. So it has been studied a lot both mainly by computer scientists, but more recently people in statistics realized that it's an important problem, and it's an important fundamental problem, and studied all sorts of variations of this. Okay? So what can we say about this problem? So how would you go about finding the set S?
K is known in this case, right?
K is known, right. So yeah, the simplest thing here is, the most immediate thing would be I go over all subsets of size K, and I check if they form a clique. If they form a clique, I say, okay, the first clique that I find, I output that. Okay? So let's call this exhaustive search. Okay. So when will the exhaustive search output the right clique? Well, one thing that you might want is that it doesn't find a clique that is there pure because of randomness, because you have k vertices that because of the noise they are all connected together. Okay, so you for sure you want k to be bigger than the largest clique in G and P. Okay, the size of the largest clique in GMP. So let's call this n, and let's try to understand how big this n here is here. Okay, Monte. All right, so what is the probability that n is bigger or equal than some integer L? Well, I can upper bound this by the sum over all possible sizes, L to n, of the expected numbers of cliques of size j. Okay? So this is what? Is n choose j. Right? There are so many potential cliques of size j. And each of such set is a clique with what probability? While with probability p, all the edges have to be present. How many edges there are in a clique? Well, there is j times j minus 1. Right? This is what, again? This is the expected number of cliques of size j in G and P. Okay? Because you have to choose a set, and then each edge has to be present. Okay? Now you see there is a fight here between this factor that grows with j and this factor that decreases with j. And the question is, when does this factor prevails on this, basically, right? So let's do a crude bound. This is less or equal than a sum from j from L to n of n to the j. And then I'll do, okay, p to the j minus 1 half times j. Okay, so this is some j l to n. Okay, let me just rewrite it as n p to the j minus 1 over 2 to the j. Okay, so you see everything depends on whether this number is bigger or smaller than 1. So I can further upper bound this by a geometric series. And then p to the l minus 1 over 2 to the j. And this is less than a constant times n to the n times p to the l minus 1 over 2 to the l. Okay? I just sum the whole geometric series. Okay? So if n times p to the l minus 1 over 2 is less than 1, I'm in good shape. This guy goes to 0 for large L. So what does this imply? Well, this means that L minus 1 over 2 log 1 over p has to be bigger than log n. So this means that L has to be bigger than 2 log 1 over p of n plus, okay, times 1 plus small of 1. Okay? So what we found is basically that the size of the largest clique in G and P is just 2 log n, where the log is in basis 1 over p. So it's very small. All right? So this suggests that exhaustive search works if k, the size of the clique, is bigger than 2 times 1 plus epsilon log. So let's say that we are taking p equal 1/2. Okay. For general p is like this. So here I'm thinking of p of order 1, of course. Okay. So this is not a proof of that fact, but basically you can build a proof based on that idea of this statement. Okay. Okay. What is the problem with exhaustive search? Well, the problem is that it takes a lot of time. How much time? Well, it will take times of order. So complexity is of order n to the k. I have to go over all subsets of size k, and this for k of order log n, this is about e to the log n square. So this is non-polynomial algorithm. But this is, from a statistical point of view, from a statistics point of view, this is the end of the story. Turns out that below 2 log n, you cannot find the clique because the graph is indistinguishable from a pure order training random graph. Above 2 log n, you can find it, end of story. Okay. So what about polynomial time algorithms? Well, it turns out that there exists a classical algorithm for this problem. Okay, so hereafter, I'll take p equal 1/2. Just for simplicity. So there exists a polytime algorithm that is a spectral algorithm. Okay, so this is a spectral time algorithm. A spectral algorithm due to Alon Krivelevich and Sudakov. So this is early 2000. So I don't remember the date. I've read 2001, but it's early 2000. And the algorithm works as follows. let me construct a modified adjacency matrix that is the centered adjacency matrix. And I'll write like this. And what is this? This is a matrix whose entry ij is 1 plus 1 if ij is an edge, and minus 1 otherwise. Okay? So I take my normal adjacency matrix, I put 1 if there is an edge and 0 otherwise. Here I'll use plus 1 minus 1 because I want the matrix to be centered to be around 0. Okay? So what does this matrix look like? Well, on S, on the set S on which I planted the clique, I will see only ones, right? Because I have all edges. Okay? So if I had only the set S, I would see 1 on S, 1 on S transpose. 1 on S is just the indicator vector on the set S. All the other entries are what? Are plus or minus 1 IID. Okay? So let me write that as W. So let me introduce a matrix W where Wij, I less than j, are IID uniform in plus minus 1. So it's just a matrix, symmetric. It's a symmetric matrix with entries above the diagonal that are just fair coins. All right, this is not the end of the story because if I do this, then I will have screwed the entries on S. So I will subtract this, what I call WSS. That is just the matrix obtained by W by setting to 0 all the entries outside S. Okay? So I subtract back the entries in S. Okay? So I have the matrix W, and I have the set S. So if W is this, WSS is this matrix here. Okay? The submatrix corresponding to entries in S. Okay? So in this way, this is exactly the centered adjacency matrix of the model that I defined before. Do you agree? All right. All right, Monte. Okay, very good. Okay, now what we know about this thing. So you have a rank 1 matrix, that is the signal really, plus noise, a matrix with IID entries basically, a Wigner matrix, plus something else. Okay? But okay, if you think a moment about this, this something else is negligible with respect to W. So we will neglect it. So what can we say about W? Well, by our little theorem before, the operator norm of W is of order square root of n. So let's say it's 10 square root of n with high probability. Okay. What about the unperturbed matrix? So if I call this the signal, x equal 1s, 1s transpose, the first eigenvalue of x of my signal is what? What is the first? It's k, right? It's just the square of the norm of the indicator vector of S. S has exactly k entries equal to 1, so the norm is equal to k. And all the other eigenvalues are 0, right? Lambda 2 of x is equal to blah, 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 lambda n of x. These are all 0, because that is a projector. So the idea of a long Krivulevich and Sudakov was compute the first eigenvector of the centered matrix. Okay, the original paper is said a little bit differently, but. And what do we know? Well, we did this calculation already in the last lecture. What happens if you have rank 1 plus noise, what you get from the first eigenvector. So using Bedin's theorem, again, we get something of this form, that V1 of the center adjacency matrix times the first eigenvector of the unperturbed matrix. So this is the vector that is 1 on S divided by square root of k. The absolute value of this scalar product is bigger than square root of 1 minus some constant times n divided by k squared. Remember, here there is the square of the size of the perturbation. This is the square, basically. This was the square of W. Okay, perhaps the constant is a bit bigger. And this was the square of the gap. The gap between the first and the second eigenvalues of the unperturbed matrix. Okay, so if k is bigger than a big constant times square root of n, the scalar product is very close to 1. So the leading eigenvector is very close to the indicator vector of the set S. So if you plot it, say, versus I, from 1 to n, this is the set S, and this is 1 over square root of k. So this, you will see something like this. This is the vector, the leading eigenvector then of the unperturbed matrix, and the leading eigenvector of the center matrix will look something like this. So what do we do with that? Well, the idea of Alon and others is the following. You compute a first estimate of S, S naught, that is formed by the k largest entries of V1. Now, this set will not be completely accurate, will not be exactly equal to S, but we can refine it. How do we refine it? Well, this will have a good overlap with the set. Right? So the claim is that S hat not intersection S will be bigger than something like k over 2 or some such number. And at this point, what you do is the following. It's like, okay, you have to put in jail to catch a mafia gang. Okay, you didn't catch it, but you caught a set that contains half of the people in that mafia gang. What do? You look at all cell phone communication and look at all people that spent a lot of time in the phone with the people that you caught. Okay? So you look for all the people, a set. So this is the set of vertices that the degree of I in the set S0, S set 0, is bigger than something, 3/4 k. if you do this, the claim is that by simple, kind of Chernoff bound, this S hat will be with high probability equal to S. Does this make sense? So basically, this second step is not really, this part is not really important. It's a combinatorial trick that allows you to reconstruct exactly the full set once you have a rough idea of where the set is. The crucial part is really the first part, and the crucial bottleneck is the first one. That is, it's even difficult to get a rough idea of where the set is. Or, the spectral algorithm gives you a rough idea of where the set is. So when does this work? Well, this whole business works when k is bigger than some constant times square root of n. Okay? So above this threshold, Alon et al. Algorithm works. Okay? So let me draw the picture a little bit bigger. You have square root of n. So above this square root of n threshold, this problem is okay from a statistical point of view, in the sense that I can find the clique, and I can find it efficiently. I can find it in polynomial time. So let me write that this is computationally okay. Below log n, this is statistically impossible and also computationally impossible. And then there is this big regime in between in which the problem is statistically possible, but computationally we don't know. We don't have an algorithm. Any question about this? Well, so far that I gave an algorithm, and this algorithm fails here. Now, a good question is, can you find another algorithm that succeeds in this regime? After all, Alon and others came up with this more than 15 years ago. Did anybody improve over their result in 15 years? And the answer is basically no. All right? So nobody could find a way to improve over this gap. Sorry?
When you test numerically, the threshold is at square root of n below.
Yeah. Yeah, so good question. So a good question is this a problem of the analysis? You were just sloppy here. You are a poor mathematician. You really don't understand random matrix theory, or it's a problem of the algorithm. And the reality is that it's a problem of the algorithm. So let me open a parenthesis here. Okay, let me open. So we could have done this whole analysis more carefully. So what does it mean more carefully? That part, WSS, can always be neglected, but then we have this centered adjacency matrix, and this is 1 on S transpose plus W, plus the small stuff. Let's forget about the small stuff for a moment, okay? And you can ask yourself, what is the threshold above which the leading eigenvector of this matrix starts to be correlated with the truth, with the true set? What is the exact threshold? Now I know I go take a lot of classes in random matrix theory, and I learn how to do that, okay? And in fact, this is basically something that I mentioned already in the last lecture, and this is this BBAP phase transition in which you have a rank 1 matrix plus noise. Right? So this rank 1 matrix is of norm k, the noise is of norm 2 square root of n. Turns out that the correlation between V1 and 1 on S over square root of k looks like this. It's 0 below a certain threshold, and the threshold is square root of n with constant 1 in front. and then becomes positive above that threshold. Okay? And this is, okay, let's say that this is k over square root of n, and this is 1. Okay? So there starts to be a correlation when k over square root of n becomes, say, if you call this lambda, bigger than 1, and this correlation, you know, I wrote it already in the last lecture, is something like this. No? So above 1 over square root of, above square root of n, for k bigger than square root of n, you get a positive correlation, and indeed you can push the whole analysis of Alon et al. To go all the way there. Okay? But below this, the algorithm of Alon, Krivelevich, and Sudakov fails. Okay? So by doing a lot of analysis, you can improve this to 1 times square root of n instead of a constant times the square root of n. Okay? Now, there is an interesting trick that Alon and others use. You can improve the constant at the cost of extra calculation by a clever trick. And what is the clever trick? It's actually a very simple trick. Is the following. Suppose that somebody gives me one vertex in the clique, one member of this mafia gang. Okay? What you do, you look at the set of all of his friends. Okay? The set is of size n over 2, but it contains k minus 1 mafia gangs, mafia people. Okay? Contains a clique of size k minus 1. So you reduce the size of the graph to look from by factor 2 without decreasing the size of the clique. You have a graph that is smaller by factor 2 without reducing the size of the clique. All right? So by this, if somebody gives you the one vertex on the clique, in the clique, you can do it when k square root of n is bigger than 1 over square root of 2. You will say now, okay, but nobody gives me a vertex in the clique, right? After all, that's the whole problem. But what I can do now is you search over all vertices in n. So you go one by one over all the vertices. There are n such vertex, okay. And for each of them, I look at the set of their neighbors. If I find the clique there, fine. Otherwise, I go to the next one. How long will it take me? Will take me an extra square root of n factor in computation. Okay? Because before, if I order them randomly, before hitting one guy in the clique, I have to visit square root of n guys. Right? So you can push this. You can pick now 2 vertices in the clique, 3 vertices in the clique, etc. Each time you are hit by an extra polynomial factor. Okay? So what you end up finding is that you can achieve a threshold that is epsilon times square root of n in time complexity n to the some constant times log 1 over epsilon. All right. So in practice, you will never use such a trick, of course, because it takes a lot of time, right? But in principle, if you are available, if you are ready to allow any polynomial time, you can reach any constant times square root of n, but you cannot go to square root of n over log n. Or this trick doesn't lead you to square root of n log n. Any question? Okay, very nice. So we tried the spectral algorithm, and this didn't succeed on this problem. Okay, so there is this very interesting huge gap between what you can do, in polynomial time and what you can do statistically. Okay, so a natural question is, can we do better? And so you all know about compressed sensing, for instance, and you all know that in compressed sensing, something that works very well is convex optimization. Okay, and the same in matrix completion. Convex optimization is a very powerful tool. This is the one-line summary of this whole area, right? Okay, so can we use convex optimization? And the most powerful way to construct a convex optimization formulation of this is to use SDP hierarchies. Hierarchies. No? So let me go over this, what it is. So we have a nice optimization formulation of this problem. We said that if you search over all cliques of size k and you output the first clique that you find, that will give you a statistically optimal solution, right? Equivalently, what you could do is look for the clique of largest size. Okay? So find the maximum size clique. Okay. So this is the algorithm. You really take the graph and look for the clique that has most vertices and output that. Okay? And this, by the same argument that I gave before about the exhaustive search, will work all the way down to k of order log n. Okay? So you can write the maximum size clique problem as an integer programming problem that is the following. I maximize the sum over I1 to n xi subject to what? I want xi to be in 0, 1. And I want xi xj equals 0 for every ij that is not an edge. This is the complement of the edge set. Let's look whether this makes sense. You see, if you find the clique in the sense that xi is the indicator vector of a clique, then what must happen, the condition for xi to be x to be an indicator vector on a clique, is that every time you have an edge, is either an edge between two vertices. So if you have an edge, it's either that both vertices are if you don't have an edge, sorry, it's either that both vertices are not in the clique, or so you don't have an edge here. So it cannot be that they are both 1. So this is forbidden. This is what this is saying. If there is no edge between I and j, they cannot be both 1. Right? Because otherwise it's not a clique. So this constraint is exactly the constraint that x is the indicator vector on a clique. We call the value of this opt. So if you can solve this optimization problem, then you can find the maximum clique. Then you can solve this down to the statistical threshold. This planted clique problem down to the statistical threshold. Does this make sense? So
what is x here? What are the examples?
the x are the decision variables. So the objective is to find the clique of a maximum size. So xi is 1 if I is in the clique and 0 otherwise. So you find the clique of the maximum size. So most of the vertices possible are 1, subject to the xi being binary. A vertex is either in the clique or it's not in the clique. So they are binary. And the x must form a clique. What does it mean to form a clique? It means that if two vertices are both 1, you cannot have an edge between them. Or vice versa, that if you don't have an edge, then they cannot be all 1. Is everybody okay with this? Okay, so this is a nice optimization problem, that if you can solve, gives you the statistically optimal solution problem. Unfortunately, it's an integer programming problem, and in general, we don't have any algorithm to solve it. But one way that we know is very successful is to construct a convex relaxation. Okay. In particular, a powerful relaxation is an SDP relaxation. That I'll now describe. Okay. So let me rewrite this problem in the following form. Let me introduce a matrix M, and the matrix M is the following. It's n by 1, so M is n by 1 by n by 1, n plus 1 by n plus 1. I put here 1, here the vector x, here the vector x transpose, and here x transpose. So I'll index the first column by the empty set, the first row by empty set, and these are all the columns 1 to n, and this is 1 to n. Okay? I just defined something. Is the gram matrix basically of my, or it's the exterior product of x with itself. Well, how can I rewrite this combinatorial problem with this matrix? Well, we want to maximize the sum over I 1 to n m empty set I subject to what? Let's see. We want m empty set I equal to mii. You see, this constraint is the constraint that xi is in 0, 1, right? Because it's telling you that xi is equal to xi squared, right? And then what else? I have that m is positive semidefinite, because m is just the outer product 1 x times itself. So it's the outer product VV transpose. So it's PSD. And the other constraint is that, of course, we have this constraint, is that mij is equal to 0 for all ij that are not edges. And finally, there is another thing, is the rank of M is equal to 1. So this is standard way of constructing a lifting of our original problem. Now, this is a very nice problem in the sense that this is a linear constraint, this is a linear constraint, this is a linear constraint, this is a convex constraint. This is a not convex constraint, but I can drop you. After all, I read a lot of papers about compressed sensing and matrix completion and all this stuff, full of people proving that you drop this rank constraint and everything will be beautiful. Why not? I'll drop that constraint. All right, now I get a convex relaxation that is a semi-definite programming relaxation. Okay, Monte. Okay, in fact, okay, now I've wrote an SDP relaxation. In fact, it turns out that this is not the best SDP relaxation that you can write. It's just one SDP relaxation, and there is more powerful ones, okay? This is, in fact, what's called the second level in the SOS hierarchy. And I'll write SOS2 to mean either this problem or the value of that problem. Okay, so this is a hierarchy of convex relaxations that is indexed by an integer, and I take D an even integer. And as you take D larger and larger, you get a tighter and tighter relaxation, a better and better approximation of the convex hull of the integer set. Okay? And for any D, you get an SDP relaxation of better value. SOS2 has a value that is larger, so this is a maximization problem, so as you get tighter, the value gets smaller and smaller. SOS2 is the first value. This is bigger than SOS4, bigger than blah, 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 bigger than SOS n, and SOS n is equal to the actual value, opt. So if I can go all the way to level n of the hierarchy, I get back the original integer program. Also, this is an SDP relaxation. Each of these is an SDP that can be solved in time. N to order of D. So it's something that you don't really want to do at home, but it's like a huge hammer. So for any constant D, you can do in polynomial time. It's a huge hammer in the sense that for this type of problem, people working in the field yet have to come with an algorithm that doesn't fit in the SOS hierarchy. Okay, so this hierarchy was introduced in the late 90s, early 2000s by Lasserre, and is sometimes called the Lasserre hierarchy, and by Pablo Parrillo. But actually existed already in some form in the Russian literature due to Namshor. Right? So this is a huge field in itself, and I don't want to, you can construct this relaxation for any polynomial optimization problem, meaning an optimization problem where your cost function is a polynomial and your constraints are polynomial. There is a systematic way to construct convex relaxation that is given by this hierarchy. So it's a machine, it's fairly easy actually. You put down inside the polynomial and spits out a sequence of relaxation, and it's completely automatic. And basically any convex relaxation or most convex relaxation that you ever saw fit into this framework, and normally are the level 2 of the framework or the level 4 sometimes, etc. So let me, now I don't want to go into this, but let me describe how this works in this simple hidden clique problem. Okay. So the decision variable now look at one thing. One can look actually also at odd level D, but for notation it's actually simpler to work with even level, and it doesn't really matter because I'm interested in any constant D. Yes?
Yeah, just a small remark for the audience. I think when you speak about the problem, you're speaking about the minimization problem, when you take the minus the picture, the right is the maximum, and then just for the...
So it's a maximization problem.
Yes, but when you look at the minimum, you have this for the order of the...
Yeah, so it's a maximization problem. So when you get, so it's a maximization problem. So when you get a convex relaxation, you get an upper bound. And as the convex relaxation becomes tighter and tighter, you get a sequence of decreasing upper bounds. Okay? So this is a picture. A better picture is the following. You have an optimization problem that is a discrete optimization problem that you start from, right? What we start from, opt, is a discrete optimization problem. It's a problem on the hypercube, right? And then we cannot solve this, so we construct an SDP relaxation that looks like this. So it's a convex set. This is an optimization problem in which we have a discrete set and we want to optimize a linear function over this discrete set. So we want to optimize a linear function over this discrete set. So you come up with a convex relaxation, and this is perhaps SOS2. Okay? But what the SOS hierarchy gives a sequence of convex relaxation. So when you solve SOS2, you get an upper bound on the real value, right? If you optimize this function, you get this point here. So it's an upper bound on the real value, but the SOS hierarchy gives you a sequence of tighter and tighter relaxations. Then there is perhaps this. And you know that as the degree goes to n, you get the original set. Does that make sense? Okay, what is the decision variable? So the decision variable is the object that I have to optimize over. It's a function x. So it's a function over a finite set, yes.
And maybe you can become SOS is a sum of squares.
Yeah, so SOS might stand for help in the sense that you try to work with this and it's a mess, but really stands for a sum of squares. That is a bit mysterious name in the way I will explain things because it refers really to the dual of the formulation that I give here. But it's connected to proof systems for polynomial inequalities. And these are proof systems that are called sum of squares. Okay, so the decision variable for us will be a function that has as domain and, okay, let me write it. So what is this? This is the family of all subsets of n of sides at most d. So this is a function from the subsets of sides at most d of the vertices to the reals. Since this family of subsets is finite, then there is at most 2 to the n of them. Roughly there is n to the d of them, actually. So this is finite, so you can think of this as a big vector. So it's really a vector of sides n to the d. In practice, d is 3 or 4, So this is a vector of size n to the 4 or n to the 5 or n to the 10, right? So this is what is the decision variable. And so this x for any such set S spits out a number that is the value of that set. And what is the optimization problem? So let me write it. Will be the following. You maximize the sum over I 1 to n x applied to I, subject to the following constraint. X of the empty set is 1, and then okay, let me write it and then explain it. M of x PSD and x of s equals 0 every time GS is not a Clique. So let me explain this. So I look at this. This is a big vector. I maximize this function. The empty set must have x equal to 1 by definition. And then I form this matrix, and I require that this is to be PSD. So what is this matrix? M of x is a moment matrix. So it's a matrix that is indexed by subsets of size at most d over 2. And the definition of this matrix is that Mx, so this is a matrix indexed by subset. So if I look at subset S, comma R, this is a specific entries of this matrix. This is by definition X evaluated on S union R. And last thing, what is GS? GS is the subgraph induced by S. So it's the graph that has vertex set S and has all edges that have both entries in S. Okay, so this might look a little bit. So how many of you, just a check, how many of you ever saw this, SOS relaxation in your life? Okay, there is a small fraction. So I'm not boring most of. So this is. So does it make sense syntactically? Syntactically, it makes sense, right? So you have a linear, you have an objective, you have a value function, you have a decision variable that is a vector, objective that is linear, a linear constraint, a bunch of linear constraints, and a PSD constraint. And the PSD is on a matrix that is obtained by basically using linear function of your decision variable. Okay? So this is a semi-definite program. So this is, it is an SDP. It's an SDP over roughly n to the d dimension, so you can solve it in times n to some constant times d. As promised. Okay. I claim that it is a relaxation. So for being a, I want to show you that it's an SDP, it's a relaxation of the original problem. How do we check that it's a relaxation? We have to check that if you take an integer vector of length n that is feasible for opt, we have to construct a variable here, capital X, that is feasible for this problem and has the same value, right? This is how we get that it's a relaxation. So how you do it? Well, we do it in this way. For every set S, you take the product over I in S of xi. And I claim that this is feasible for this business here. Why? Well, first of all, this objective is exactly the same objective as before, because x of entry I is just xi. So this objective here, if you do this setting, reduces to the objective that I had there. Second, x of the empty set is 1, of course. And third, this is satisfied, right? Because if lowercase x is feasible for that, then it is an indicator function of a clique. If you take any set that doesn't induce a clique, you will get in the product at least 1, 0. Okay? So all the linear constraints are satisfied by this ansatz. You have to check one more thing. You have to check that this is PSD. How do you check it? Well, let me define a vector V that is of dimension, okay, that is indexed by subsets of size at mod D over 2. Then if you look a little bit at it, so what you obtain is that matrix M of X under this definition, entry SR of this will be what? Will be the product. Let me define a vector. Let me define this vector. And the way I define is that Vs is just equal to product over I in S of Xi. So this thing is just the product over I in S union R Xi by definition. And again, by definition, and since the variable are 0, 1, this is the same as VV transpose. And so it's PSD. So this setting is satisfied, it's feasible for this problem, hence this is a relaxation. Does this make sense? Notice that this thing that this SDP actually implies in subtle ways a lot of inequalities that you would like to have on your variable. If you start thinking of this, you start thinking, okay, perhaps I can strengthen this SDP if I add this linear constraint. And turns out that typically they are all implied by the hierarchy itself. For instance, let me give you one example of this claim. And the example is the following. Okay, perhaps I'll come down. Tableau 2. For instance, if first to look at this, you might say, okay, very nice convex relaxation, but I can get a tighter thing by requiring that my variables are between 0 and 1. Turns out that this is directly implied by the hierarchy. Why? Because if you look at your moment matrix will contain at some point contains a submatrix that is the following. There is a submatrix of my moment M. It's called the moment matrix. It has a submatrix that is the submatrix that corresponds to the empty set and the set S. And this submatrix looks like this, right? 1 XS and here XS. right? Because here there should be x of S union R, but S union R is the same as S. Right? Now you want this submatrix to be the PSD, because M, you impose that the original M was PSD, therefore this submetric is also PSD. But what does it mean that this matrix is PSD? It means that XS minus XS square is bigger than 0. But this is exactly, this is the function x minus x squared. So this is exactly the statement that XS is between 0 and 1. So this constraint is actually implied already by the hierarchy. And there is a bunch of other constraints that are implied. Now it's also easy to check that the naive, in the simple case there, is just the SOS2 level, right? In that case, we had number for each pair of vertices. We put a new number for each pair xi, xj. Now, does this work? So, no, a natural thing, since there is this big gap, there is a big gap between what you can do statistically and what this spectral could do. We have this big hammer that is the SOS hierarchy. Let's try to check whether the big hammer works. If it works, we found an algorithm. If it doesn't work, well, we have some evidence that this is really a hard problem. The question is that we cannot prove NP hardness by reduction because this is a statistical problem with a probabilistic model. So it's very difficult to do reductions. So there are not many ways of proving hardness for statistical problems. One of the few that is useful in practice is to take a big class of algorithms and prove that all of them fail. So there were at least 5 or 6 papers dealing with this question for this very specific problem, and the question was settled in a very nice paper by Boaz Barak and a group of 6 or 5 other authors. So Barak et al. In 2016. So this was really spurred by a paper. So there was an original paper by Avi Vigdarsson and Raghu Meka that claimed a result. But then people discovered that there was a gap in their proof, and then people tried to fix the gap, and this was fixed eventually by then, and they proved that SOSD fails for k bigger, k smaller than square root of n. Now, I don't know what is here, but I think it's log n to the d. I don't remember exactly the result, but I think it's stronger than that, but let's say it's that, unless d is bigger than a constant times log n. Okay? So this basically says that even this big hammer fails, doesn't give you large improvements. So above log n, the question. So you remember that the complexity of the hierarchy is n to the d. So above log n, this means that you have to take n to order of log n, which is e to the log n square. Okay, it doesn't matter what it is. But this is the same that you can achieve by exhaustive search. If you remember, exhaustive search takes complexity n to the k. Since the relevant k is log n, exhaustive search always succeeds in times n to the log n. Right? So this doesn't gain even anything over that log n.
which a hierarchy would actually, doing more than 2 levels will improve? Or is it like a general phenomenon that never works?
Yeah, this is a general phenomenon somehow that now it's not something that is proved or of which there is any understanding. Okay, there are some problems that are very specific. For instance, if you look at tensor factorization, so you have a n by n by n by n tensor of order k. Then if you look at the second level of the hierarchy, basically gives you nothing. So the first non-trivial level that gives you something reasonable is that you do something like the kth level of the, so if you have a tensor of order 3, you have to go to the third or the fourth level of the hierarchy, and everything below gives you something trivial. But in all of this problem, there is a natural level, the first non-trivial level, quote unquote, and above which you don't get an improvement. Now, it is likely that you get improvements on the constant. And the other thing that happens is that you can improve if you allow for doing time that is exponential. So there are problems in which if you allow me to do e to the n to the epsilon time, I can move the threshold by factor into the delta of epsilon, right? So I don't know if this has been proved but it has been proved in, so there is a work by Prasad Raghavendra and Selil Shram that looks at the tensor factorization, and they prove that if you do the hierarchy, so you do the hierarchy with n to the epsilon level, then you can improve an n to the minus, I don't remember, delta of epsilon factor in the kinds of statistical threshold. Right, so, but you have to go to very large levels to do it. But this is, there is not a really nice example in which you go to the fourth. The second level does something non-trivial. You go to the fourth and you get a large improvement. Yeah.
What exactly do you refer to failure of in this particular theorem?
Okay, so what they prove, we'll see actually an example of this, I think, in the next lecture. But what they prove is the following. You see, if you solve the original integer programming problem under the pure Erdos-Renyi, you get log n, and under the planted model, you get something much bigger, k. So what they prove is that if you do the SOS hierarchy, you get under both model, you get square root of n. So you will not be able to distinguish, even to distinguish two graphs, whether they come from one case or the other. You see, a natural, a simpler question than the estimation question, or at least an intuitively simpler question, is the following. I give you a graph, and the graph is either has a clique inside of size k, or doesn't have a clique, and I ask you, which is this? So this is the hypothesis testing problem, right? And one way to address this problem is to say, okay, I'll solve my optimization problem. I know that under the null is log n. I know under the alternative is k. If you get bigger than k over 2 something, then I say I reject the null, right? Now, okay, this you have to solve the actual optimization problem. What they look at solving this with the optimization problem, and they see instead that under both the alternative and the null, you get something much bigger, square root of n, right?
So this failure is with hypothesis?
Yeah, it's of course it's with a probability. So this is all average case. Okay. Okay, so as I was saying, so this was done originally for the case of d equal 4, and then these people were able to extend it for any d. The case d equal 2 is really a toy case. That is the case that I gave you here. Already the case d equal 4 is quite complicated. So I think in the next lecture what I'll go is that I'll show you how what does it mean to prove something like this in the toy case of d equal 2, and this should give you some understanding of what all this is about. Okay, and yeah, I guess this is a good moment to stop. Thank you.
question?
So we ignored the WSS. We ignored the WSS in the analysis. So at what size of K does the...
Well, you see, I mean, for the spectral method, if you think of the analysis of spectral method, this is again a Wigner matrix, but it's a Wigner matrix of size of dimension K with entries of order 1. So the norm of this is square root of K. And the norm of this is square root of N, and the norm of this is K. Right? So this is always negligible compared with those guys.
Other questions? Comments? No? Okay, so let's thank Andrea again.